Okay, this looks good. All right, good morning, everybody. Welcome to Tuesday morning pre-calculus. What I'm going to do is today is basically a walk down memory lane with word problems, and then maybe work some of our attention into some basic inequalities. So this will be more of a reminder of what you did in your pre-calculus days, well, actually college algebra days before pre-calculus. So if you found that you had to do a lot of review last week, that's a good thing, because that just usually means that you're getting back into a routine of doing lots of algebra skills that you did not only in college algebra, but in algebra 2 in high school. So let me go ahead and share my screen. Let's see if I can get to the other. That's not the one that I want. Let me get this one. Let's see here. Well, I lost my other screen for my notebooks. Let me see if I can find it. Just 1 second. Okay, so let's see. 225. Oh, I guess I didn't save it, or maybe let me check here. If not, I'll just go ahead and give you the problem. Oh, here we go. Let me X out all of these. And let's see. I don't need that, so that'll work. Okay. So let me try this again. So can you see the word problems on the screen?
Yes, sir.
Okay,
Yes.
good. I'm trying out this OneNote just so you don't have to watch me write everything. And so OneNote gives you a lot of whiteboard space, and I think this will be a good way to do it. So here's what I want you to do. What I've done is I've typed out a lot of just routine word problems. So the first one I want you to copy is the very first one that you see here. It's called a rental company charges $50 per day and 20 cents per mile for truck rental. These are problems that you have that are similar to your WebAssign problems. And then it says Michael rents a truck for 4 days and his bill is $286. Then the question is, how many miles did he drive? So go ahead and think about that. See if you can set that up. This is a very basic problem, but I want us to get our minds moving with this. So I'll give you a few seconds to think about that, and we'll work on that. But make sure you have this copied. Again, a rental company charges $50 per day and 20 cents per mile for truck rental. Michael rents a truck for 4 days and his bill is $286. How many miles did he drive? So go ahead and think about that. Now let's look at the solution. Now, what we can do, it doesn't really matter how you set up your variables or whatever. you can usually just use your favorite letter. I like X, but they can also be, you know, whatever you decide. So now notice that we had a bill of $286. And so now, for instance, we're also given 20 cents per mile. So we can say 20 cents is just 20 over 100 in terms of dollars, or just 1/5 dollar. So this would imply that if we look at this particular equation in terms of X, 1/5 X would be equal to 286 minus the fraction that was spent, and as we say, on the per day rental. So notice 4 times 50 will give us $200. And another thing that we notice is that if we have the amount here, we can then subtract it from the 286 to know how much was spent on the actual, how much was driven, the actual number of miles. So take this and go here. Now, this is where the problem is very useful. We know the rental was for 4 days. And that's how we know what number to put here. Again, this is a very straightforward problem, but it's a very good problem in organizing your thoughts. And so now we have 1/5 X, and this is obviously very simple, is equal to 86. And then of course we can multiply by 5. So that'll give us a 30 and then a 3. So if we look at this, that'll give us 430 miles driven. So the idea with these types of problems, as we will merge into the mixture, the time, rate, distance, and the fraction of work, is to just get an idea of how you set up logic. And with these types of problems, there is no fixed way to do them. There is no standard way. Now, with the other types of problems I mentioned, I have my own standard techniques, which I think make them easier. But in this particular problem, all you have to do is put together the given information and then solve the problem. And that, again, can be done many ways. But again, when you're solving a word problem, we're basically translating everything into numbers and equations. And from that information, decipher some type of solution. Now, let's go back to the next problem that we have. So I'll go back to my OneNote. Now, here's another problem again before we start the mixture problem. This is the second problem. This says Ben, again, another type WebAssign problem. Now go ahead and write this down. This says Ben invests, and that's money here, sorry. Ben invests $3,500 at 4% annually. That is 4% annual interest. How much additional money must be invested at 5.5% annual interest to ensure that the interest he receives each year is 4.5% of the total amount? Now, most students read this and say, Professor Ryan, I'd rather do a mixture problem. This is too many words. So first, what I want you to do is we can use X for the additional amount of money. That's the easy part. What I want you to do is take the 4%, the 5.5%, and the 4.25%, just like I did with the 20 cents, and write them as fractions. So right now at your desk, take the 4%, take the 5.5%, and the 4.5% and write them as fractions. You think about that, then I'll show you my work. Go ahead and do that now. And I'll say this, don't reduce them. We want to keep them all nice and clean so we can use some symbolic computation. The symbolic computation is our friend because it allows us to get rid of factors without having to do so much arithmetic. Okay, so I'll go ahead and go back to the screen and I'll share with you what I've done. Now, here's the approach that utilizes the fractional arithmetic to make the problem easier. Most students, again, if I worked with some of you with the WebAssign, and then there was an occasion with the fish population problem where we actually approximated the square root because the actual number of years came out to be an irrational number. So there are times when we need an approximation, and that certainly serves us very well. But in most problems, we work the problem exactly until we are asked or requested to make an approximation, or we need one just to move the problem to some type of approximation that will benefit the reader. So what I was talking about is this kind of computation. 4% by definition is 4 divided by 100. I'll stop with that. I'll explain why I did this. 5.5%, well, that's 11 over 2 divided by 100, which is 11 divided by 200. So again, just making the mixed number into an improper fraction. And then, of course, if you like here, I can just go ahead and say this is 11 over 2%. And of course, this would be 9 over 2%. So when we write the fraction here, we get 9 over 200. And here we get 11 over 200. So these are not reduced. If you recall up here, I reduced this because there was no reason not to. We only had one fraction, and that made sense to do that. But here we want to do symbolic arithmetic. Now, because all of these denominators are 200, I'm going to go ahead and convert this one to 200 and get 8 over 200. Now, like I said before, if x is the additional amount, and if you look at some of the practice tests on the Blackboard site, I think this was one of the problems that I put on the test. It's become fairly famous, at least in the type of technique that I use to solve it. And so now you've got this amount here that you started out with. The problem said Ben invests $3,500 at 4%. So that's the amount right there. 4%, 8 over 200 times 3,500. And then the additional amount here is X at 5.5%. So that's 11 over 200 times X. And this needs to be equal to 4.5% the total amount invested. So here, this is the total amount invested. So amount invested. So we want to know the additional amount that must be invested at 5.5%. So 4.5% of the total amount invested equals that. That is, at the end of the year, he's able to make this much in interest. So again, the problem, you know, maybe not that interesting to you, but again, as a mathematical problem, it has its merits. So now notice what we have here. We have a very simple linear equation, but we've got fractions that are going to be simplified by the fact that we have all these common denominators. So now again, if you read the problem, we've got everything set up. So now we can look at this like we did in the previous section in 1.5. Let's multiply through the entire equation by 200 to rid ourselves of all these horrible denominators. So multiply by 200. So this gives you a very efficient way to do this problem and a very good way to teach it. So when we multiply by 200, all these 200s absorb. So we get 9 times x plus 3,500. Do this all symbolically as much as we can to avoid excessive arithmetic, equals 11x plus 8 times 3,500. I don't need to multiply any of this out because I've got copies of 3,500 over here, so I'm not going to waste my time doing that. Now multiply everything out. 9x plus 9 times 3,500 equals 11x plus 8 times 3,500. Now at this point, all we want to do is just get the like terms on each side. So we can subtract 9x from both sides to give us a 2x. And now this is where we use the distributive law, the algebra. Here we have 8 copies of 3,500, and here we have 9. So we subtract 8 copies from 9, that leaves us 1 copy. So we just have 3,500. So this is what I term symbolic computation, where we use the algebra to do the most work for us without having to multiply excessively. And now we can look at this and say, well, we can just divide by 2, and that's doable. So that'll give us a 1, and then we have a 14 or 15, so that's a 7 and then a 10. So now we see that, what was the guy's name? Ben? Ben needs to invest an additional $1,750 at the 5.5%, so that the total interest he receives is 4.5% of the total amount invested. That is, now you see that by converting all of these percents to usable fractions makes the problem simple. What I've noticed, and this is not, this is part of, you know, the calculator generation. Computers are wonderful. That's why we're meeting virtually now. But excessive use of calculators where you don't need them is really not good. For instance, some of you will do numerical analysis at the university where you use advanced calculus techniques to solve numerical problems, and so there's a need for that in certain applications. But you don't throw the calculation device onto a problem unless it's required. And so this gives you a very clean way to do the problem using the symbolic computation. So again, this is not really that important of a problem, clearly, but the techniques that we use to solve it reminds us of what we did in college algebra when we would clear denominators. Remember, you know, you can have variables in the denominator, or you can just have numbers. It's the same work. The number theory and the algebra are basically the same. There's no difference. When number theory was studied for so many hundreds of years, when the algebraists came along, they were just basically switching out the letters because the work that was done in both fields basically tied together. And then they figured out that geometry was pretty much the same thing as algebra and number theory too. So there you go. Now,
I have a question.
yes.
why did you put it over 200?
Oh, right here.
Yeah, like why'd you put 11 over 200, 9 over 200, and 8 over 200?
Oh, okay. Well, the definition of percent is the number divided by 100. So if I divide this by 100, I get 11 over 200, right? And if I divide 9 over 2 by 100, I get 9 over 200.
Oh, okay.
That's just to write the percent as a fraction, so we avoid a bunch of messy decimals.
Okay, thank you.
So Kaylin, this is important in that this gives you an alternative way to do this problem. You can do this problem with the decimals, but then that kind of clouds the arithmetic process. But yes, everybody know Kaylin's question is very good. Practice deciding how it is you work with percents. What is a percent? What is a percent? It's the number divided by 100 by definition, okay? So now let's look at another example. What I want to do, ladies and gentlemen, is to introduce some new techniques, okay? I want to give you some new techniques. I don't want to just do the same old stuff you've already seen. Lots of my students will say, well, I learned that from Professor Ron. The idea here is that you keep what you know, you use what you know, and then hopefully I can give you some additional concepts to add to what you already understand to make the process even better. I think that's really what it means to learn, so to speak. And so feel free to use these techniques, or feel free to use your own. As long as the result is correct, we're good to go. Now, look at the next problem. This is a mixture problem. And in the WebAssign, they don't really give the name label TA and TB. I just put those in there to make it a little bit easier to understand. So let's read this problem, and I'll have you look at it for a few seconds to try to set it up. This is a standard mixture problem. We have a TA that sells for $4.05 per pound, and you're thinking, you know, Professor Ron's going to get rid of those decimals, so we make it like the last problem. And then TB sells for $2.65 per pound. Okay, so we can write both of those as fractions and use the same technique we used in the previous problem. Then it says blend the T's to produce 70 pounds of a T to sell at $3.55 per pound. So maybe you work at Starbucks and your manager gave you a raise because you knew how to do this problem. And that's good. I mean, you know, let's face it, you can use your college algebra in many instances. Then it says how much of each type does the merchant use? Okay, so in this particular case, and if you recall your work in college algebra, you just simply know that you have to let X be one of the pounds of the T. So let's work it that way. I think this will come back really quickly. And these problems are not very difficult. They're actually kind of fun. So now when we look at this particular problem, again, we have, let me just go ahead and paraphrase. We have TA at, and this is what we think of as a concentration, $405 per pound. And then we have TB at $2.65 per pound. Again, thinking of that as a concentration. Now, at this point, all you have to do is just let the pounds of one be represented by the variable. So we'll say let X equal pounds of TA. Now, mixture problems can be done many ways. I have a technique that I set up when I was my first semester at the North Campus when I was teaching an intermediate algebra class. And I set up these techniques to help them understand it. And of course, they stuck because they were just as good for my college algebra students. So if we have X pounds of TA, and we know we have a total of 70 pounds, this implies 70 minus X pounds of T type B. So TB. Okay? So now, when we actually do these problems, this is how I would set these up. These aren't fraction bars, these are just blanks. And this turned out to be very useful. So I've got my first blank, TA, TB, and then the blend. So I've got my concentration here, but I'm going to write this as a fraction, and I'm not going to reduce it so I can easily clear denominators. So my concentration will be 405 divided by 100. That is writing the concentration as a fraction, which is nice and clean. I'm going to do the same for TB. That's going to be 265 over 100. Again, you see I'm going to clear the denominators with the 100s, and then of course use some symbolic arithmetic. And then over here, what is the new price will be $3.55 or $3.55. So I'm going to say 355 divided by 100. So we're going to think of these as concentrations. Now I'm going to fill in how many pounds I need to absorb the pounds. How many pounds do I have of A? I've got X. How many pounds do I have of TB? I have 70 minus X. And how many pounds will I have of the blend? Well, that'll just be the 70. So that's the equation right there. You don't have to do two equations and two unknowns or whatever. What I tried to do was think of this like I do fraction of work problems, where you basically have a way of combining two things, mixing two things, and then describing the mixture with a concentration and amount, concentration, amount, concentration, amount. So what we would say here is that the cash is preserved. Now we have a problem like we had in the previous example, where we've got these common denominators which are just in the way. So multiply by 100. Now, like I say, this technique may be different from what you did in a previous class, but I will tell you that this is easier. It's much easier, less work. So we get 405 X plus, go ahead and multiply this out, 265 times 70. Do it symbolically, don't multiply it, just do it symbolically. Plus, minus 265 times X equals 355 times 70. We have to do some arithmetic, but it's very simple arithmetic. Now we can combine, let's go ahead and combine everything. We're going to have 405 minus 265 times X. That are these two terms, these X terms. And now over here, I've got copies of 70 and copies of 70. So this will be 355 minus 265 times the 70. So the only work we have to do is just the difference here. So 5 from 5, that's 0. And then we have a 4. And then, of course, a 3 minus a 2, that's a 1. So we get 140x. And then over here, 5 from 5 is 0. And then we basically have a 15 minus a 6, which is a 90. And then that's it, times a 70. So the only arithmetic we had to do was this. Once we convert these into fractions, and again, you must resist the temptation to reduce. If you've got a bunch of fractions in a problem, in an equation, then you want them to all have the same denominator, especially if you're adding and subtracting. Because if they don't, then you got to go backwards and get a common denominator, which is really not what you want. So there, it takes a little bit of getting used to. But now notice this is easy. The zeros here absorb. So we have 14x equals 90 times 7. I like to do the arithmetic in my head and skip the step, right? And now we can divide by 7. So here that's going to be a 2x equals 90. And then we can divide 90 by 2, and that's 45. So what you do here, ladies and gentlemen, is, again, divide by 10. The 70 becomes a 7. The 140 becomes a 14. Now divide by 7. The 7 becomes a 1, so I don't put anything. The 14 becomes a 2. And now we can see we can just divide 90 by 2 and get 45. So what does this imply? Well, we go back up here and we see that this means 40 pounds of TA. And then we can just subtract, this says 70. Oh, sorry, 40. Yeah, I think Professor Ron should just write down the number that he computed, 45 pounds of TA. And then now if we work this out, 70 minus 45 will give us 25 pounds of T type B. Now, the reason, and again, it doesn't really matter. The numbers can be less nice. The numbers can be less nice. And so that's always an issue with word problems. But for the most part, when I ask you to do a word problem, the numbers will be reasonably fair in the sense that if you utilize the techniques I've given you, you should be able to come up with responses that are manageable, so to speak. What we want to do in these types of problems, again, this technique will work for any kind of blending or mixture problem. Again, you have the concentration times the amount. And of course, we're assuming that we're really good in the laboratory, that we're not wasting anything. And I don't make paraphrases about that. Obviously, these problems are idealized, but that's what you do. Some of you will become project engineers, and you'll have to set up procedures for certain productions. And in those procedures, you'll have to make some adjustments for the fact that individuals may make mistakes and throw out stuff. So when we do our mixture problems, we assume that we're being really tidy in the laboratory. So again, be sure to make sure that when you do your fractional arithmetic, that you make sure all the denominators are consistent, and then you just get rid of them. So again, the common denominator here makes the problem easy. Resist the temptation to reduce. We always like to reduce things, but we have several types of fractions here that are added and subtracted. We need the common denominator. Okay, let's look at another example. Now, again, this type of problem is similar to what you did in your college algebra class. So let's go back to another. Yes, sir.
I have a question. When you were absorbing the 0, why was only the 70? Why did only the 70 lose the 0?
Okay, well, I divided by 10, right? So if I could choose to lose the 0 on the 9 or the 7, your choice. If both of the zeros were lost, that would be division by 100, and I didn't do that. Do you see?
Sir.
Yeah, isn't that interesting? Thank you, Jose, you get 10 points. The idea here is that we've got products, and so when we divide, we have to make sure that we are actually dividing by the single number. And so what Jose is noticing here is that I could have divided the 90 by the 10 and had 9 times 70. Your choice. The same response, but just make sure when you've got products that you're only dividing one of the actual factors. It's like saying this. Here's an example. Say we have 2x equals 4 times 8. Okay? So now when I divide, I can just say, well, I'll just divide the 4 by 2. So that gives me x equals 2 times 8, or 16. Well, the thing is, because this is written as a product, I have to be careful about division. Now, if I had written that as 32, then you say 32 divided by 2 is 16. But when you write them as products with factors, you have to pick one. So that's just a way of breaking down numbers. So Jose, that was an excellent question. Thank you. Now, let's look at another example. See, the idea is that when we have interesting type problems that make us look at things differently, it makes us a little bit more aware of how we can add new ideas to problems. Now, of course, I've got my mistake here. Let me make the D into a G. I like this little OneNote here. There are all kinds of bells and whistles that you can use with virtual teaching. And of course, I like my document camera from Japan, and I like my Wacom tablet. But this OneNote at least gives you a nice whiteboard. Now, before we do the time, rate, distance, I want to bump down to the radiator problem because it's similar, like a concentration type problem like we did with the T, and then come back to this. That way we can kind of focus on the fact that we're dealing with concentrations. So again, this is another type mixture problem that's very common in the college algebra and pre-calculus sequence. So let's read this. Go ahead and write this down in your notes. It says a car radiator contains 65% antifreeze. It says a suggested concentration for the summer is 50% antifreeze. Then it says the radiator has a capacity of 3.9 liters. Now, how much solution should be drained and replaced with water to reduce the concentration? So this might be for you chemistry experts, something that you do in the laboratory. Also you biology experts, and then of course sometimes in physics you obviously deal with equation and kinematics and things of that nature. I would say that this is a good problem to know how to do regardless of your field of expertise. So the idea here is we're thinking of concentration, and we want to be able to make an adjustment so that we can make the concentration lower to maybe agree with what the manufacturer likes. So here's what I want you to do at this point is I want you to take all of the percents and I want you to write them as fractions, don't reduce, and I want you to take any decimals and write them as fractions, don't reduce. So go ahead and do that now, just like we did on the last problem, and then we'll compare notes. Like I said before, resist the temptation to reduce. We want everything to have the same denominator, or at least something manageable. And you can pick your favorite letter for the volume of solution to be drained. You can use X if you want. So I'll share my screen. Now when we look at this, it's just like the last problem maybe in the context that we write the 65% antifreeze as 65 over 100. That's a simple concentration. The 50% as 50 over 100. And then the 3.9 liters, I just write as 39 over 10 for a convenient fraction. Of course, we can't reduce that anyway. And so now what we want to do is look at the fact that when we see here, X is the volume of solution to be drained. That tells us how much of this we're going to have in the final solution. So here's what we have to do. Let's go ahead and write in our concentrations. And this is how I used to teach my intermediate algebra students. They liked it. They said, "This is easy, Professor Ron." I said, "Well, that's the whole idea. I want you to understand it." And notice here, the water doesn't have any antifreeze, so that's 0% antifreeze. And I'm writing this here so you don't think I just ignored it. Well, it is a term, but it's not going to have any impact. And so we can keep our procedure consistent. Now, when we look here, we think, here's the concentration. What's the volume? Well, here we have 39 over 10. So we have a nice simple fraction, 3.9 liters. And now this is the key here. How much of this am I going to have left? Well, I'm going to have the 39 over 10 minus the amount that I drained. And then I'm actually going to replace what I drain here with water that has no antifreeze in it. Okay, so even though this particular term here doesn't have an impact, it still should be written so you can actually do these problems consistently. So this tells me how much of the 65% I will have when I do my mixing process. And this gives me the final concentration amount, so to speak. So the idea here is that when you work out these problems, just like the cash per pound or the antifreeze per liter, it's all done the same way, no difference. Write your concentrations with very simple numbers. Now, of course, we're lazy, so we're going to multiply by 100 to clear the denominators. Now, here's, and then you're thinking, well, wait a minute, Professor Ron, what about the 10 here? So I can make a little adjustment here to make it a little bit easier. Let's see here. In this particular case, let's see what I want to do here that will actually make it easier. Let's do this. Let's start by multiplying by 100, and then we'll make another adjustment since I said this first. So let's multiply by 100. So we get 65, 39 over 10, minus x, again, this is 0, equals 50 times 39 over 10. Just to keep everything simple the first time through. And now what we can do, I'll do this in 2 steps to make it a little bit easier. Now let's multiply through by 10. I think the 1,000 was a little bit complicated and I want to keep it simple. So now let's multiply through by 10, and that's going to annihilate that and give us a 10x here. So we have 65, 39 minus 10x equals 50 times 39. Now, if you see here, the work here that we did with the fractions obviates any need to work with decimals. Students always think, oh, I've got to use decimals. No, the arithmetic is made much easier now using the fact that we've cleared denominators. Now we can use some symbolic calculation. So we have 65 times 39 minus 65 times a 10x equals 50 times a 39. Now what we want to do is get our copies of 39 on one side and our x on the other. So let's go ahead and factor. So we'll have a 39 times a 65 minus 50. So again, we subtract 50 copies of 39 from 65 to give us this. And now take this over, and this gives us 65 times a 10x. Now we can see that the difference here is 15. So this is 39 times 15. Now we can go ahead and do some factoring here. I'm going to write this down one more time, then we're going to do some factoring to make it simple. Notice 39, this is what you do in your intermediate algebra in number theory. This is 3 times a 13. And 65, well, that will be what? 5 times a 13. So now we can replace that. So we have 3 times 13 times 15 equals 5 times 13 times 10 and times an x. So now we can see that the 13s absorb. And also we're going to get an absorption of a 5. But let's just go ahead and write down what we have. 3 times 15 equals 5 times 10x. And now we can go ahead and rewrite some of these. We got a 5 in the 15. So this is a 3 times a 5 times a 3 equals 5 times a 10 times an x. And so now these will absorb. So now we're left with simple numbers. 9 equals 10x. And you didn't have to pick up a calculator, you just used number theory. So x is equal to 9 over 10. So now we see that we need to drain 9/10 of a liter and replace the same amount with water. So drain 9/10 liter of 65% solution and replace with 9/10 liter water. So what I want to show you here is that mathematics is done, algebra, number theory is done symbolically. And what I want to show you here is that the more practice you take in breaking down numbers and seeing how they interrelate to simplify the equation is a much better way to prepare you for the calculus. When you get to calculus, you have to be able to work with variables and arithmetic when you do limits, when you do Riemann sums, when you do optimization problems. And what I'm finding is students do not have an ability to work with the number theory and the algebra. When you were in grade school and general math, you did prime factorizations all the time. You broke numbers down all the time. Then you stopped doing it, which is really unfortunate because we see here that this problem can be solved just by breaking down the numbers. Now, of course, as you work through the process, you can streamline some of this. I put down all the steps to make it clear what I'm doing. When I work the problem, I've got 3 lines here, and here I've got 3 times that many. But the idea is I want you to be sure that you understand what I'm doing. And what's nice here is that if you break this down into 2 steps, you can easily see that we now have an equation with no fractions, and then we use symbolic arithmetic to actually find the solution. So the main thing that we see with mixture problems is the setup is always the same. We could be mixing more than 2 quantities, but normally I'll just test you on the mixture of 2 solutions, whatever they may happen to be. And then we have the desired concentration, so to speak. So this will always be the setup, and you can always label each blank to give you an idea of how you are to move the problem forward. So the blank labels just tell you what you need to do. And of course, the fractional arithmetic just helps you to be a little bit cleaner as you work these out. Let's say this, as you help your friends that need assistance with word problems, show them that they can solve these problems using their basic understanding of number theory. And when you do that, they're going to come away with a better understanding. And then, of course, after you taught it, you will come away with a better understanding. Okay, now let's go back to that problem that we left out. And that, again, that's going to have a lot of arithmetic in it too. That's why I like to do these. So let's go back to our OneNote. Now, this is the one that we passed over, but you can see it's got some nice fractions in it. And that was the reason I decided to do some of these. These are straight from your WebAssign. And they give you good practice working with the symbolic arithmetic. Now let's read this. In this particular case, it says that Wendy took a trip a distance of 330 miles. So this is time, rate, distance. Remember, D equals rate times time. When we get to calculus, we'll do variable rates. She traveled by bus and train. Okay, so the bus drove, well, that's a nice leisurely bus. The bus drove 30 miles per hour and the train speed was 65 miles per hour. The trip time, and so we're not saying there's a lag time between the bus and the train, you know, magically she gets on the train with no loss in time. Of course, this is idealized, but that's okay. The trip time was 7.5 hours. Then the question is this: how long did Wendy spend on the train? Now, here's what I want you to do to set up this problem and do it in a way that will be good. I want you to convert any mixed numbers to improper fractions. And then I want you to do a chart. That is, I want you to do a time, rate, distance chart where you have a row for the bus and you have a row for the train. Okay, go ahead and do that and then we'll compare notes. There's only one mixed number to write as an improper fraction, so do that first. This will be a good practice to see if you've been listening to me. Okay, let's see what we have here. Let's do some comparison. Now what I've written here, again, my favorite letter is X. I guess you could use a D, but the main equation here is distance equals rate times time. And since we're given some times here, let me move Professor Ron over a little bit. There we go. Here's our equation, D equals RT. And so T is just what? D divided by R. Very simple, but actually quite important. So now what we know in this particular problem is that we have a bus leg of the journey and we have a train leg of the journey. We know the rate of the bus is 30 and the rate of the train is 65. Now, I don't know the distance traveled on the train, what we're asked to do, if I read the problem, is how long did Wendy spend on the train? So the distance on the train we can define as X, and then like the last problem, we can do a subtraction to actually get the distance for the train. So remember, the total distance in this particular problem was 330 miles. So if this is X, we can just do the difference, 330 minus X. Now, students always look at this and say, why? And of course, when we add these two expressions, we get 330. So this distance must be this. So kind of like the mixture problem we did before the radiator problem. And now what we can do is do the ratio of D divided by R. So this chart, I remember when I started, I did this in my intermediate class. And then of course, my colleague, Nate Wiggins, did the same thing. We always liked the books that use the charts for the time, rate, distance problems, because we thought that was the mark of a good book. And we both have found that this type of procedure is a very nice organizational one, just like what we use for mixture problems. And so now we say D divided by 30. So we get X divided by 30. And now here, again, D divided by the rate. So we have 330 minus X. I mean, at least we don't get a quadratic in this case, but we get some unruly denominators divided by 65. So again, the times for each leg of the journey we have, and we know what the trip time was. It was 7 1/2 that I've now written as 15 over 2 hours, just to convert the mixed number into an improper fraction. So this implies that we have X over 30 plus 330 minus X over 65 equals 15 over 2. Now, you look at this and say, well, Professor Ron, that's linear in X, and I agree, but I want you to do this problem symbolically. That is, I want you to clean it up as far as the fractions go. So what we want to do is treat this like a college algebra problem where we actually break down the denominators and do this symbolically. So the first thing we want to do is some little arithmetic on the side. So let's do some breakdown, so to speak. Now let's start with 30. 30 is 6 times 5, right? So that'll be 2 times 3 times 5. Let's just get some prime factorization so we can get a least common denominator. I did this for all of these, I believe. And then 65, well, we remember that from the last problem. That's just 5 times 13. Do your little factor tree. And then 2 is 2. Okay? So what we want to do is get a least common denominator, just like we're in a college algebra class, to convert this to a nice equation with no fractions. So we do LCD. And again, we just start with the first number and write down all the distinct factors and any multiplicities of those factors. We need all of that. So we need a 2, a 3, and a 5. So we're taking care of that, that, and that. Don't put slash lines through anything. Underline them or put a check above them. Don't slash through anything. That is the worst notation in the world, and I will never do that. Now here, we've got the 5 right here, so we don't need to repeat it. It's not like it came in a multiple of 2 or a power of 2, so that's taken care of, but we don't have the 13. So now that's good. Now we go here to 2, and it's just a 1 power. We have a 2, so that's taken care of. So the least common denominator is 2 times 3 times 5 times 13. Okay, so that's what we have to multiply the equation by to clear the denominator. So let's do that. So we'll do 2, and don't multiply anything. Leave everything factored. That's the problem. Everybody multiplies everything just to go forward, then to have to go backwards. Now what I want to do to make it easier is go ahead and factor the denominators as I've done here. 2 times 3 times 5. And then 330 minus x, and 65, 5 times 13. So again, we're going to do this symbolically. And then 15 over 2, well, we're going to get a lot of stuff hanging out, but that's okay. So we'll have 2 times 3 times 5 times 13. And now just to make your notes a little bit better, you know, all this is recorded and we put this on the link on your Blackboard site. Just put a little box around that because that's kind of important. Again, the numbers and the variables are all the same, ladies and gentlemen. There's no difference. And so treat them just like you've been doing fractions from your general math days. Now when we do the symbolic, we see the 2, the 3, and the 5 here absorbed, and we're left with the 13 times the x. Now, what's interesting about all of this is that with the symbolic calculation, we do a minimal amount of work. We still have work to do, but it's certainly a lot less doing it this way. Now notice the 5 and the 13 absorb, but we're left with the 2 times the 3 here. So this will be plus 2 times 3 times 330 minus x. So we want to do minimal arithmetic and let the algebra take care of everything. Now over here, we've got a lot of numbers, unfortunately. The only thing that absorbs is the 2. So we get the 15. And we got another copy of 15 there, but I'll factor this, leave it factored, and then we can compare with what we have on the other side. Okay, so when we look at this, we're thinking, okay, now we can just go ahead and collect terms. We've got copies of x here that we can get together. So now we've got a 13x plus, and I'll go ahead and write this as a 6 times a 330 minus a 6x. So we've got those two terms, and then we have the stuff over here, which is nice and factored. Again, I'll put this as a, I'll go ahead and write this out as a 3 times a 5, get the 2 copies there. I won't write powers, those are harder to see. Okay, and then of course with the 330, let's just do a little computation here to see what we have over in this case. This is going to be a 33 times a 10. So that's a 3 times an 11, and that's a 2 times a 5. So that's the prime factorization of 330. So now we get what? 7x when we combine these two guys. That's easy. 6 from 13. And this will be 3 times 5 times 3 times 5 times 13. And then we subtract this guy with our factorization. And that's going to be 6 is 2 times 3. And then we have 2 times 5 times 3 times 11. So basically we want to divide this by 7. So now we can go ahead and reduce all of this. Now let's look for prime or common factors here. Notice we've got a 3, so underline everything that's common. We've got a 3. We've got a copy, another copy of 3, so underline that. We've got a copy of 5, so underline that. Now, of course, we have another copy of 5, which we don't have here. We have a 13, which we don't have, and clearly we don't have an 11. So now let's remove the 3 times the 3 times the 5. And when we look at that, that leaves us with 5 times 13. Now over here, we remove the 3, the 5, and the 3. That leaves us with 2 times 2 times an 11. Again, 2, 2, 11. Everything else is taken care of. So we have 7x, 3 times 3. Now inside, we just want to get a difference here. That'll be easy enough. So this will be, they don't have any common factors. So this is 65. And then of course we have a 44, 4 times 11. Sorry to get a little crooked here. So we have 7x equals 3 times 3 times 5. And then here, when we do the difference here, we're going to get what? A 1 and a 2. Well, so there's our factor of 7. So WebAssign was good to us. Okay, that's going to absorb this 7. So x equals 3 times 3 times 5. And of course, 21 is 3 times 7. So the 7 goes, that absorbs. And so we have what? 3 times 3 times 3, that's a 27, times a 5. You think I should just leave it factored? You know, why am I doing this? Because I'm just going to go backwards anyway. So yeah, leave it alone. So that's the distance, and it's actually 135. That's the distance that the bus has traveled. And then if I check back in my notes, it says that how long did Wendy spend on the train? So now let's just go ahead. Since I've got a 330 up here that I'm going to need, I'll go ahead and write this as a 135. And then later on, if I need the factoring, I'll do it. And so now we can say time spent on the train will be 330 minus x, in this case is 135, divided by 65. So that's easy arithmetic. That's a 5. And then, of course, that'll be a 9, and then a 195. Now, of course, this, again, thank you, WebAssign. 195 is 3 times 65. So this gives us a 3. So now we see that Wendy spent 3 hours on the train. Now, again, you're thinking, well, Professor Ron, I could just, you know, I could run this, all these numbers in a calculator, and I could do that and divide and whatever and get an answer, and maybe that's all in good. But again, you've lost all of the practice of factorization. Why have I found this to be effective? And this is how I taught when I taught my intermediate algebra kids back when I started at San Jac. They all went to college algebra and they passed. And they would look at me at times and say, boy, I never thought math was like this. And what I'm trying to show you here is that when you work out problems, maybe you get to the point to where nothing has a common factor and all the numbers are, as I would term them, kind of ugly. They don't do anything for you. And maybe you don't get a whole number, or like in the last problem, you get 9/10, which is a fraction. I mean, again, not a whole number. It still allows you to work through the problem and allow the arithmetic to do the actual execution for you. Because when I do all of this, I'm doing algebra. And when you do calculus and analysis, you do algebra. It's like when we do sequences in mathematical induction and we derive the formula for an ellipse or a hyperbola. We will use these types of factoring techniques. And it's the same thing with the letters. It's the same thing with the numbers. So the idea here is when you get to a point like here, again, this is a simple linear equation, which we can now work through symbolically. Now, I'm not saying you have to do this every time, but I'm trying to teach you some techniques that are going to help you get better. And when you get to calculus 2 and you're solving infinite series problems with Professor Ron, or you're computing a surface area, or for instance, you might be trying to find the area of a polar graph that's enclosed by a polar graph, you will use these types of techniques because the ability to work with numbers is important in executing limits, derivatives, and most importantly, integration. Integration is extremely difficult. Differentiation is simple, but the techniques of integration are much, much more difficult, and they require an ability to work with numbers. So good for us. Now, I want to share with you one more example, and then we're going to talk a little bit about inequalities. And this will be quick. Now, I've got two problems here. Let's just go ahead and do the swimming pool. I think I've got this over here. And then we'll move on to some basic inequalities. But I wanted to spend some time with these problems to give you an opportunity to look at the solution a little bit differently. Again, if you can't do mathematics without being tied to computer algebra systems and calculators, then I don't think you own what you do. The idea, ladies and gentlemen, is that the techniques of engineering, mathematics, computer science are the same as they've always been. And they require the ability to work with numbers and algebra. And that means with pencil and paper. So be careful. And then when you start writing your beautiful programs, you'll be doing the same thing, picking on a computer using your logic. So now look at this particular problem. It says Bob and Jim fill a swimming pool. This is the famous fraction of work. And of course, Professor Ron has his method for these too. It says the job for both hoses is 18 hours. That's what I mean, the job to fill the pool. If you use both hoses, the time is 18 hours. Then it says Bob's hose is 50% more efficient than Jim's hose. That means, you know, a quicker process. Then it says compute the time for each hose to fill the pool alone. Now, here's what I want you to do before we compare notes. I want you to assign a variable. You can use T, and I want you to figure out, in this particular case, the time that is required for Bob and the time that is required for Jim in terms of a variable T, and then we will reciprocate it. So go ahead and do that first. So like I say, assign T as your variable, and you can assign it in this case for the time for, I think what I wrote here, time for Jim if you want. So see what you get with that, and we'll compare notes. These are so much easier than the previous problems. You're going to be mad at Professor Ron. Why did we do this first? That's okay. You do the hard problems first, and then everything else is easy. So let's compare some screens here. Again, as you're working with your friends, share these techniques with your friends and help them. If you can provide, it's just like Professor Ron's AC lemma for factoring quadratics and quadratic form. If you understand that method, then you can teach that to your friends who cannot factor well, and they will get better because it is an efficient technique that is easy to teach, and it is a beautiful, beautiful result. Now, here's what I did, and of course this is your choice. I'm using T here. And I'll show you my technique to work these out, which is, again, something I devised when I taught the intermediate algebra. So I'm going to let T be the time for Jim, for him to actually complete the job. And so for Jim, I say job in T. It's actually hours, but I'm not going to put H there. That clouds the situation. And then Bob is 50% more efficient, so he's going to take half the time that Jim does. So that's how we interpret that part of the problem. Now, the key now is to now write fraction of the job per unit time. So this is how I taught my students. You reciprocate this. So you get 1/t fraction of the job per hour. And then you get 2/t fraction of the job per hour. This again makes the problem more commonsensical. If you follow some of the techniques in the books, they don't make any sense. That you reciprocate things and then students can't really understand why they do it. Well, now here's a simple way to set up this problem. So we have two contributors. The complete job is 100%. So the right-hand side is always 1. That's 100%, 100 over 100. That's the complete job. And who do we have? We have Jim and we have Bob. And they're both going to work for 18 hours. So I say fraction of the job for Jim is 1 over T. You're going to laugh at how simple this is. We need a simple problem with easy numbers for a change. And the fraction of the job per unit time for Bob is 2 over T. And we're given that they both work for 18 hours. Like I said, maybe we should have started with this because this is trivial compared to the last one. So we have 18 over T. Now we've got here, we've got 36 over T equals 1. So the same denominator. So no symbolic calculation here. So that'll give us a 4 and then a 5. 54 over T equals 1. So now, of course, if we reciprocate both sides, again, this was easy. T equals 54. Oh, let me not put my units too soon. So as we go back up here, if Jim works alone, it takes him 54 hours. So this implies that, and we'll just say time for Jim. So this implies 54 over 2, which will be 27 hours, will be time for Bob. You're thinking, we started out with all these problems that had all this arithmetic in them. If I had started with this one, you would have been much more happier with me. The fraction of work problems by nature of how they're constructed are easier. The arithmetic is simple. The opportunities for the symbolic computation are minimal, but you can see that when you think of the contribution of each person being added to give 100%, this gives a paradigm, so to speak. This gives a model for solving any fraction of work problem. And so what that means is that maybe you might have 3 people contributing and you have another term here. So this is actually one of the simplest word problems that you do in college algebra. And if you set it up this way and actually figure out the times and reciprocate them, that is fraction of work per unit time. That's why I call these fraction of work. Such a blessing to teach intermediate algebra for a year at San Jac. Both my colleague Nate and I did it for 1 year, and then they moved us into academic completely. But I will say this, I remember those students well, and boy, they worked really hard. We weren't using WebAssign at the time, we were using MyMathLab, but then I made the conversion to the WebAssign. So again, what I want you to do with your WebAssign is to practice the problems with some new ideas and new techniques. Use what you already know and then add to what you know to see if you can actually move the process forward in your mind. That is to improve your competence. And again, what's important here is if we compare the problems that we've done, in all of these problems, we have symbolic computation, symbolic computation, symbolic computation. And it makes the problem streamlined and it doesn't tie you to a calculator. And this way you can go back and easily check your work. So again, that's what I want to impress upon you, because you've seen these problems before. I'm sure you probably saw most of these problems in Algebra 2. So this is maybe the 3rd or 4th time you're going through this. Now, what we want to do is look at some simple applications. And when I say simple, some ideas about inequalities. We've been studying equalities. So I want to make 2 comments about some ideas that basically differentiate the inequality from the equality. And here's one major theorem. So this is 1.8 in your WebAssign. And now we're going to go back and revisit this back in, I want to say chapter 5 No, actually, it's chapter 3 when we do theory of equations. And we will revisit some of these techniques. I just have another section there for you to practice with this again. But all the techniques that you're going to need, we're going to do now. This is really what we call basic inequalities. Lots of times it's good just to revisit things. And again, with inequalities, I'm all for what you already know. Basically, what I want to do is give you some additional ideas and make sure that what you do is correct. Don't ever do anything when you don't feel confident. Always use techniques and steps that you understand and feel good about. So here's one particular theorem that we want to stress. And you probably learned this in Algebra 1. Suppose A is greater than B. And now, if you look at this, when someone, and we're assuming these are real, when someone writes C less than 0, you know that means C is negative. So another way to say this is C is negative. Now, again, when A is greater than B, we know that the difference A minus B is positive, but we don't know what the signs of A and B are. That's not given. So again, when we look at this, we say, okay, A is greater than B and C is a negative number. Then here's the result that you've known, I'm sure, for probably over a year. Then A times C is less than B times C. And basically what this result, and this is indeed a theorem, you can prove this. If you multiply or divide an inequality, well, division is multiplication, so that was a little bit redundant, but you know what I mean. If you multiply an inequality by a number less than 0, okay, as we have here, when you're dealing with real numbers, you reverse the sign of the inequality. Now, the idea here is that this is not hard to prove, and I probably will say more about this as we move on through the course, because I've hit you with a lot of new ideas today. But for instance, here's a simple example. If we're just dealing with numbers, we'll say 5 is greater than 2. And you believe that. And now I'll just take, for instance, C to be negative 3. Then this implies that 5 times a negative 3 must be less than 2 times a negative 3. But if we just fill all of this out, this is negative 15 is less than negative 6, which is true. And of course, that's not a proof, clearly. That's just an example of what's going on. Now, as you've noticed here, we do symbolic calculation. When you're working with numbers, you often don't forget about reversing the inequality. But when you're working symbolically, you might multiply by a variable that's less than 0 and forget to switch. So that's what's important here. Just remember, multiplying by negative numbers or even variables or expressions that are less than 0 for some given values of real numbers, you must also remember this. So I'll just say, this is, I'll just say, put on a note card. It's kind of like the quadratic formula. This is something that you will use now and forevermore. Calculus, my goodness, you take advanced calculus, maybe linear algebra, differential equations, topology. Anytime you work with equations, you're going to be using this. And again, it's easy to forget, but don't sweat it. Probably the more times you make the mistake will help you to remember it. Now, there's another theorem that I want to talk about. Now, of course, we have office hours today from 3:15 to 4:30. So if you would want to come by office hours and we'll talk about this a little bit more, I'll be glad to. Another thing, the inequality deals with absolute value differently. We know what it does with the equality, but suppose now that C is greater than 0. So we know that this notation means C is positive. C is positive. And we can easily prove this too. Then How does the inequality react with the absolute value? Well, the first one is called the conjunction. Now, this has become a rather old term, but I still use it, and it's important to be able to call it something. So the conjunction will be some variable in x. We'll just write x now for the purposes of our theorem. If the absolute value of x is less than c, then this is equivalent to the compound inequality. This is used in the theory of limits. So this is something you will use quite often in Calculus 1. It is indispensable. So we have x between the additive inverse of c and c. So this is what we call the translation theorem, so to speak. That is, if the absolute value of x is less than c or equal to, you won't change anything, just put equals to here, you will have the equivalence of the compound inequality. That is, x lies between c and its additive inverse. So when you see this, you can interpret it as this. This is important. So when you solve basic inequalities that look like this, again, the form here is required. The absolute value must be isolated, and you must have a positive number here. Then you can write this and solve the compound inequality. The other one is called the disjunction. And it's actually a little bit easier to prove, but easy to remember. This will be x in absolute value greater than c. Now, sometimes the you know, when you write this down, it may not make any sense. I mean, you know, it doesn't mean that, oh, wow, you're just going to get this beautiful solution. That is, if a solution actually exists, then it will be equivalent to this. Just realize that not every inequality has a solution. You can sometimes find typos on tests where the students don't have any work to do. I've subbed before, and I'm like, well, kids, do your best, but I don't think you're going to get an answer. So just remember that these are equivalent in as much as there is a solution. So this will be x is greater than c, or x is less than the additive inverse of c. This is what we call the disjunction, the conjunction combined compound inequality, the disjunction separated. So when the absolute value of the expression is greater than the positive number or positive constant, we get x greater than c or x less than c. This reminds us of the equality. Remember when we have x equals c, we did this last week and you all did fine with your WebAssign. This is x equals c or x equals the additive inverse of c. That is the expression here inside the argument of the absolute value may never be negative. So, I mean, this won't have a solution. So if there is one, it'll be found this way. So that, I know I'm beating a dead horse, but just keep that in mind. So this kind of compares where we have absolute value of x greater than c, we have x greater than c or x less than c, and it compares to the equality where we can kind of line these two up. We have the or statement. So when you think about the disjunction, think about what we did last week. And when you think about the conjunction, this will probably be something that you talked about in college algebra. And if you didn't, that's okay. Now you know. And so this will be used. It is part of the definition of the limit in calculus. It is indispensable. So we'll say calculus 1. Actually, all of them. Calculus 1, 2, and 3. This is a very, very important result and has high utility and is completely efficient. Now, let's do some simple examples and then we'll talk about Professor Ron's BV technique. The boundary values, again, when you're doing inequalities, I'm going to show you a nice technique to keep up with sign. Now, I want to do a couple of, just one with the conjunction. So we have 5x plus 3. I just made this up. Is less than 1/2. Again, the point here is not to trick you. Sometimes, you know, I'll write something down and I'll say, can we solve this? And do we use the definition? Just remember, when we think about the definition of absolute value when x is real, this can be written as a function defined in two pieces. That is, this is x when x is non-negative, greater than or equal to 0, and it is the additive inverse of x when x is less than 0. So what we're seeing here is that by definition, the absolute value of x is always non-negative, always. And we get that for free. So if this doesn't apply, then we may have to go to the definition. Professors always say that, well, I guess we have to use the definition. And of course, my students say, oh no, if we have to use the definition, we have to work harder. Well, usually you do, but that might be all you have. So let's look at this example and we'll just say solve in the real numbers. Now, what we want to do when we notice this is that we do have an absolute value here and we have a positive number. So when we go up to number 1, we see we have the absolute value of 5x plus 3, where x has been replaced by this expression. And then we compare, we have a c of 1/2. So this is table ready, so to speak. This satisfies the theorem hypothesis. So we can say use theorem. Again, if we have a quadratic equation, we have to write the equation at least with all the variables on one side so we can identify an A and a B and a C. That is, we have to be able to satisfy the hypotheses before we apply the result. Otherwise, the result, there's no guarantee that it will be correct. For instance, you can get lucky, but there's no guarantee. So now we say, okay, well, we can use the equivalence here. So equivalently, we have the additive inverse of 1/2, which is negative 1/2, less than 5x plus 3, less than 1/2. So we basically write what the theorem says. And again, during office hours, if you would like me to say a little bit more about this, I will. If we have a slow day, which we probably won't, I'll go into some more detail about this. This requires some nuances with inequalities, and I don't think at this point we're really ready for that. But those of you that are interested to see more about this, please come to the office hours and I'll give you some ideas about how you would work into it. Now, what we can see here is what the attempt is to isolate x between, that is, have a lower bound and an upper bound. And the first way to do that is to subtract 3. That is, we want to first isolate the 5x. So we have negative 1/2 minus 3 is less than 5x plus 3 minus 3 less than 1/2 minus 3. So I'm doing a lot more steps here than I normally would do, but this is new. And so it's good to write in all the steps. Later on, you can leave and consolidate. So now just remember that 3, just get a common denominator of 2, is just 6/2. So this gives us negative 1/2 minus 6/2 less than 5x. Of course, these absorb to give us 0. Less than, now we have 1/2 minus 6/2. This is basically where we're trying to make this look really nice, in the sense that we can go ahead at this point and add the fractions. Now you're thinking, Professor Ron, you could just have multiplied through by 2, but that really is not going to get us where we want to go, because that's still going to put more of a coefficient on x. So I would not recommend that at all. So now when we subtract, we get negative 7/2. And here we get 1/2 minus minus 6/2, which gives us negative 5/2. So we don't want to go forward to go backwards. So again, as you work these problems, make good choices. If you do too much work, that's okay. More work is better than an insufficient amount of work. And now what you can see is that we've got this compound inequality. We do the same thing to each expression. Now to isolate the x, we divide everything by 5. So this will be -7/2 divided by 5. So I'm putting all the steps in now. And of course, 5 is a positive number. Multiplying by 1/5, division by 5. Don't have to worry about reversing the sign. So now when you look at this, we're going to get -7/2 divided by 5, invert and multiply. That gives us a -7/10, x, and then a -5/10. Of course, now that's just a -1/2. So you can write this if you want, or leave it the same. Just go ahead and leave it the same. That way it's easy to compare the numbers. You know, reducing things is not always important unless WebAssign tells you to. So of course, if WebAssign barks about this, then you change it to a -1/2. But equivalently, we see that x, let's write this in interval notation, x lives between -7/10 and -5/10. So again, one nice thing about having the common denominator is it very easily allows you to assess magnitude. So there, it's not always the case that I'm going to say, okay, reduce all of this. We're finding that when we solve equations, we want the same denominator. So there may be fractions that are not reduced, but that's going to help us move the problem forward. So again, the work with the compound inequality is review, but it may be rusty. So practice here, including all the steps, and work through slowly. And remember, if you multiply or divide by a number less than 0, a negative number, be sure to reverse the order of the inequality. You will forget this. I'll raise my hand and say, I forget this. There are times when I'm thinking, my goodness, Professor Ron, you know this, but we're all human, ladies and gentlemen, and that's really what makes us better. If we make the mistake enough times, we remember it. And as we get back into the routine, we'll make it less and less. Now, I want to give you an example of an inequality that is a little bit different in the sense that we don't have an absolute value and we have powers of x that are quadratic. And so how is that going to change how we do the process? And I want to share that with you. And I'm sure you've done this before, but it doesn't matter if you haven't. This is a good technique that works very well. And I'm going to give you some ideas that we're going to talk about later when we discuss polynomials a little bit more, which you, again, I keep saying did in college algebra. So we have x squared greater than 4 times x plus 8. Now, what we want to do is solve. This is simple, but I'm going to show you the quickest way to do it and an efficient way and a correct way to do it. Solve in the real numbers. So one nice thing about positive and negative, we know that the additive inverse of 1 times the additive inverse of 1 is positive 1, so to speak. The additive inverse is absorbed. And we know that if we say -1 times a positive, we get the additive inverse of 1. So an even number of additive inverses give us positive. An odd number gives us negative, so to speak. And so we have to remember that. And these are really nice qualities of real numbers, okay? We live for this. I mean, that's probably one of the first things your Algebra 1 teacher told you. All right, kids, a negative times a negative is a positive. They absorb, so to speak. And so if we want to be able to utilize this and compare a number relative to 0, we have to create a 0. So when we have an inequality like this, the first thing to do is to put everything on one side. So we're going to say x squared minus 4 times x plus 8 greater than 0. Because if we can always compare a real number to 0. This basically says now that any value of x that you substitute here, the result must be positive. And then you're thinking, well, Professor Ron, I can guess some answers. And you know what? You could probably do a really good job of doing that. But what we want to do is find all real numbers. So we don't want to have to guess unless that's the only possible way to do it. Some problems require that we start with a guess, and that's the only way we can get the ball rolling. Now let's go ahead and simplify this. We understand inequalities, at least in terms of sign, and we also understand quadratics. So x squared minus 4x minus 32 is greater than 0. And now you're thinking, oh, well, Professor Ron's AC lemma. This will easily factor. We have AC is equal to 1 times the negative 32. I mean, you can see this. I don't even have to do this. The 1 doesn't really matter, but now we can just use a negative 8 and a 4. So this will be our W, and this will be our Z or our Z or our W. I told you the order doesn't matter. So this factoring by grouping, we can do it side. So this is x minus 8 times x plus 4. Sorry, that 8 doesn't look too good. Let me clean that up a little bit. Make my snowman. My students say, oh, you make your 8s like a snowman. That's the only way I like my 8s to look. I always do it that way. Now, this is where we can look at this in terms of a quadratic polynomial, or we can do like a sign test. Now, notice, this is a quadratic with leading coefficient 1. So as x approaches infinity and negative infinity, this gets arbitrarily large. So what happens at the zeros here? Notice here, now we can write what we call BBs, or boundary values. When we look at expressions and we're trying to evaluate an inequality where we have a 0 here, we need to figure out the zeros or the real numbers for which the expression is undefined, because that could be a transition point for the sign of the expression. That is, where it's 0 or undefined. And so now we can see that this particular expression will be 0 when x equals 8, and 0 when x equals negative 4. Now, when you think about the number line, and this is maybe thinking more like polynomials, we have a negative 4, and we have a positive 8. Notice the multiplicity of each of these is 1. So when you think about what's going to happen to the graph, here it'll be above the x-axis, it'll cross, and then above here. And that's just thinking about the multiplicity. So that's usually the simplest way to do these problems. But you might think, well, how could I do it if I didn't remember that? So you could think, all right, well, you can take a test point, say like a negative 10, obviously less than negative 4. You could take a 0 here, and then you could take a 10 over here. And then all you have to do is analyze the sign of this. Notice when we replace x with a negative 10, this is a negative times a negative. So the idea here is we write, if you like, go ahead and write the factor form above the number line. So we'll do our test point. We put a negative 10 here. That value is negative. I don't care what it is. And the value here will be negative. 2 negatives make a positive. That's a check, but we already know that the graph is above the x-axis, so that works there. I mean, we already knew that. Now here we know it's going to be negative. Let's verify. If we replace x with 0, the result is negative. And 0 here, we just get a positive 4, so that's plus, so that's negative. So no luck, which is what we knew using the multiplicities. And now, of course, with the 10, replacing the x with 10 gives us a positive 2. And the x here with 10, again, another positive number. So this is plus. So lots of times I tend to focus on the test point and say, oh, okay, that's probably a quick way to do it in a way that keeps you happy and all. But multiplicities of zeros, and even where it's undefined, also gives you a method. But when you start getting more zeros, students don't feel as comfortable. And I completely understand that. But this is such a simple problem, I just wanted to say something about it. So in general, when we solve these types of inequalities with polynomials or later rational expressions, we'll do one of those soon, we can do a sign test. Now notice the -4 and the 8 make this term 0 or make this term 0, and 0 is not greater than 0. So these get an X. So it's like follow the check, so to speak. So the number line here will say now if and only if X is an element of what? -infinity to -4. Union, now we have what? 8 to infinity. Now, what's interesting about this particular problem is that it's basically an adaptation of what we did when we solved equations. For instance, if we had this equal to 0, we go here and we say, okay, Professor Ron's lemma, X equals 8, X equals -4, we're done. But we up the ante one. So we still have to use AC, even though you probably could have just done this in your head because the leading coefficient is 1. But once we have that, we look for boundary values. We look for zeros of this expression. We look for real numbers for which it is undefined. So lots of students will say, oh, wait a minute, if it's undefined, that makes it 0. No, it doesn't. Undefined is just that. You don't know. So what we found with this example is that there are no values of X for which it's undefined, but there are clearly 2 values for which it is 0. And what we know is that there is a possibility that these are transition points for sign change, okay? And what we found with both of these points is that at -4 and 8, the sign does change. And we also found, where is it positive? Greater than 0, here and here. But between the 2 boundary values, it's less than 0. Now, again, this is very important. If we have a strict inequality here, and we can include equal to 0, then we would have these as checks. So here's a little extra. What if we had X squared greater than or equal to 4 times X plus 8, okay? So we just changed it up that much. Everything's the same, but now, instead of these getting X's, they would actually work because they would make this 0. So this would say X minus 8 times X plus 4 greater than or equal to 0. All the work is exactly the same. We get the same result here, but now we can include 0. So this would imply, or this would be equivalent to X element of -infinity to -4. And then of course we use a bracket to include the -4, or now include the 8, bracket 8 to infinity. So again, you can take a problem and make a small little change and change the answer. Oftentimes when you're working word problems, at least includes a number. So students will do a strict inequality when they see the expression at least. If it's at least 5, then something is greater than or equal to 5. They leave out the equal to. So remember that it does not change the crux of the problem. It just simply impacts possibly some endpoints, some boundary values. So what we can see here, if we change the problem from this to this, we include 2 more real numbers in the solution set. So what I want to do on Thursday is do some more inequalities and then talk about functions and the definition of a function and ranges and domains. So hopefully today you were able to see that it was more like college algebra in the sense that we were going back over specific techniques that you did in college algebra with maybe a little twist from Professor Ron to get you to think about things. Now, what's important here, at least for this class and for the entire semester, is to treat this review of college algebra like new material. That is, do not say, I've done this before, I don't need to study. That is not the way to approach it. Set up good study habits and work hard so that when we get to trigonometry, when we get to conic sections, when we get to sequences and induction, we get to binomial theorem, you'll have already set up a good study pattern. The unfortunate thing is that if you see something you've studied before, and I'll raise my hand, we've all been there, we just back off and just do a minimum. That's not the way to do it. Treat this like you're going to have to tutor someone and focus on refining your techniques. And so when you do your word problems, add some techniques that I've taught you, add some symbolic computation. It doesn't mean that you have to do it. It just means that if you want to improve and refine your algebraic and number theoretic techniques, you will have to implement some new ideas. I think a topologist from Texas A&M said it very well. He said, Ron, I've given you lots of new techniques. Do not expect to master all of them in one day. He says, use them little by little and grow. And I've remembered that. That was even what my professors at Carolina said. They said the same thing, even though I was just a little person and maybe didn't understand it completely. But again, take the techniques, work them in, amplify what you know, and then most importantly, take the time to go ahead and help others that are possibly struggling. So now when you look at your WebAssign, you'll see 1.7, 1.8, and 2.1. So go ahead and start working on those, and you'll have your homework due for that next Monday. And then of course your homework due or the quiz due on Tuesday. So I'm going to try to keep that set up for the entire term. So we have the lecture, and then you have that week to learn the material, and then you have your homework and your quiz at the beginning of the next week. And this will hopefully keep you on a schedule so that you will always be consistent with your work. I want to thank you for attending class today. I think what's important here is that we have the opportunity to get even better at the techniques that we've learned in college algebra. So you all have a wonderful day, and maybe I'll see some of you at the office hours today. Take care. We'll see you on Thursday.
Have a good day, sir.
You too.
Good day, sir.
Thank you. You all have a good day. Do some math and help some people learn math. That'll make you better.